Welcome to today's lecture on fluid inclusions in minerals. We have been discussing about the the principles behind microthermometry of fluid inclusions, and starting with the very simple case of the aqueous inclusions being trapped in a homogeneous condition, could be either in the liquid field or in the vapor field, and we will discuss about the situations in which the fluid will be inhomogeneous, and what will be the situation and what will be the nature of fluid inclusions and what will they indicate in the subsequent classes. So, we will just okay. So, in continuation of what we were discussing in the previous class, we will try to rationalize the entrapment of aqueous inclusions and the post entrapment phase change that we observe in them, and the way we see them in room temperature as a combination of phases in heterogeneous condition, how it actually takes place. So, let us consider a condition corresponding to temperature and pressure P1 and T1 within the liquid only stable field in the Petit space. I am only considering, or I am only showing the boiling curve here because of the simple reason that any mineral forming process in the subcrustal condition happens at temperatures higher than at least 50 degrees Celsius or even much more than that. Conditions corresponding to sub zero or much lower temperature, it is not possible for minerals to grow, and so we will consider the situations which are most common, and we will talk about situations which are less common or exceptional later. So, let us consider that here, just at the shown as the arrow, a mineral is growing here, primarily precipitating from the fluid after it attains saturation. And let us say that the within that solid lattice of the mineral, this packet of fluid, this fluid has been encapsulated. Now, this is in a one phase condition. As per our assumption, this particular fluid, this particular inclusion will continue to remain in its one phase condition all through, and will follow a constant density, constant volume, constant composition path, which is the isochore. Which is the isochore. And now, so it will continue to move on this, which we can say that is the isochoric path. It will continue to move. It may just immediately after the entrapment of the fluid, or even a considerable time gap, even in terms of millions of years or hundreds of millions of years, which is generally the case. So, as and when it moves along the isochore, it follows the isochoric path, and it will continue to do so till the point that it intersects the boiling curve as shown on this arrow over here. So, as and when it intersects the boiling curve and reaches the point, let us say that point corresponding to that is P2 T2, and right at this point here we observe that there is a post entrapment phase change that is taking place here, and a vapor bubble is nucleating. It is always much easier to understand with respect to this phase diagram, or it also can be explained on the basis that because the liquid has got a higher coefficient of thermal expansion than the host solid. So, the liquid will contract faster than the host mineral, and the vacuum that is created because of the differential contraction of this liquid, the vapor phase will nucleate. But it will always be better or more easy to understand in this way that as and when it intersects the boiling curve, the vapor bubble nucleates, because it is essentially the condition of coexistence of liquid and vapor. Now, let us consider any other pressure temperature condition on this, because any further decrease in the pressure at temperature will make it move only on the liquid vapor coexistence curve. It cannot move away from the liquid vapor coexistence curve, because any amount of further contraction of this liquid will only make the vapor bubble to grow larger in its size. And let us talk about a situation which is P3 T3 is corresponds to the temperature and pressure is 1 atmosphere that we see in our laboratory, and the temperature is room temperature, and at which we see that this fluid, the originally trapped inclusion, which was a homogeneous inclusion, is now observed as an inclusion with a liquid and a vapor bubble. And we know why this vapor bubble has got a darker boundary, and this bright part is the central part of the vapor, and this is the liquid. Now, similar situation can be visualized in case of a situation which is the vapor this is the vapor field, and let us say that the condition corresponding to this is P1 T1 in the vapor field, vapor stable field, and here the solid host is either crystallizing or recrystallizing, growing, overgrowing, or any kind of annealing process that is going on here, and this vapor is entrapped within the mineral, solid lattice of the mineral. So, and this vapor, because the densities of the vapor is usually very low, so it will always be a very shallow or a very low dP by dt slope, yet still it will on the way that with a further decrease in temperature and pressure condition, it is also going to eventually intersect the boiling curve at a point corresponding to P2 T2 as shown here. So, as and when it intersects this vapor which is entrapped here, as and when it intersects the boiling curve, a thin rim of liquid will appear, or liquid will nucleate, because essentially it is a condition corresponding to liquid and vapor coexistence. Similarly, as discussed before, with further fall in the temperature pressure condition and till the time that we see them in the room temperature, we can only see that the liquid, the content of the liquid or the proportion of the liquid has only marginally increased, where it has been shown in a little exaggerated way just to make it more clear. So, what happens here is that this originally trapped vapor on intersection with the boiling curve has given rise to a nucleation of the liquid, and finally it is present as also as a liquid plus vapor combination. But the only difference between the case which was discussed on the previous diagram, here we get a vapor bubble which is proportionately much larger compared to the situation where the entrapment is from a liquid field. Since we have been talking about the situation that it is the water is never a pure water, the water is charged with dissolved electrolytes, and the electrolyte is dominantly, in most of the cases, is sodium chloride. So, it would be worthwhile to look at this diagram, which is a very simplified diagram. Essentially, it could be a situation corresponding to if we take the compositional variability, it should be a diagram on which we should be able to plot temperature, pressure, and weight percent of NaCl or XNaCl or mole percent of NaCl, whatever we might put in. But then if we try to see the situation in a 3-dimensional diagram, it might become a little difficult for us to visualize. So, this diagram is in a way that it is kind of distorted, and what has been plotted here, as you can see here, this is temperature and pressure, and as you can identify, this point is the triple point of water corresponding to temperature of 0 degree and pressure of about 0.01 bar, and what we just showed before, the liquid vapor coexistence, the boiling curve culminating at its critical point of water, that is CpH2O, which is 374 degrees Celsius and 218 bars. So, as we know that as sodium chloride and water are soluble in all proportions, so the critical point of pure water, and here this point, which is the critical point of sodium chloride, is temperature of the order of 3300 degrees Celsius. So, they are likely to exhibit a continuous critical curve, and this critical curve, that means if we take water, pure water, the critical point will be at 374 degrees Celsius, 220 bars, and we all know from the colligative properties of solutions, if we have this particular water having dissolved weight percent NaCl, say 5 weight percent NaCl, then the critical temperature is going to be elevated. So, this curve, black curve, which is the locus of the critical points. So, that is how we see that the two critical points could be continuously joined, the situation coming from pure water to pure NaCl. That is what I was just telling, that it could be better be plotted on a 3-dimensional axis on pressure, temperature and composition, but for a better understanding we can always look at this diagram. Now, the other part of the diagram, if we look at this point, which is marked as E, which we will discuss a little bit later, this corresponds to the freezing point depression of water when sodium chloride is there, corresponding to a eutectic proportion of the mixture. And now, since this particular point, which is the triple point of pure NaCl, means where there will be liquid plus vapor plus solid NaCl oil coexisting, this point is marked over here. So, this, if you join the point, the eutectic temperature of liquid water and sodium chloride and the triple point of sodium chloride, this will uniquely define this field where liquid plus vapor plus H is halite. Halite is actually sodium chloride. So, this field will be the liquid plus vapor plus halite, and the dark or the gray part. So, now on this as we cross this particular line to higher temperature and pressure condition, the halite will not be stable here, it will be liquid plus vapor field, and this is the boiling curve, and this triple point of water, which is 0 degree Celsius to the eutectic temperature of water, will uniquely define the field in which the liquid plus vapor plus ice will be stable. So, most of our microthermometric measurements and most of our calculations have to take into account, even though we do not need to understand the phase relations from pure water to pure NaCl, because most of our crustal fluids will be containing NaCl of the range of 30, 40, even 50-60% of weight percent of NaCl, and while calculating the volumetric properties, because this is what one of the important exercise that fluid inclusion research involves. In order to understand the behavior of fluid inclusions and to understand the microthermometric data, their interpretations, it is very essential that we understand the volumetric properties of these kind of mixed salt water systems, and what happens to the volume. So, these phase diagrams help us in understanding that. So, now from the situation that we have been dealing so far is corresponding to the higher temperature side and the understanding the basic principles in terms of the entrapment, because entrapment is essentially at higher temperature pressure condition. From the conditions of entrapment till the point or till the temperature and pressure conditions in which we are seeing them in the laboratory in a situation where it is not homogeneous, but heterogeneous with a liquid plus vapor or a liquid plus halide can be understood in this from these diagrams. So, what actually possibly in these diagrams in which you have shown, we only have talked about an entrapment process which will be only resulting in a situation where it will be a combination of liquid plus vapor at room temperature. But we know that a situation also corresponds to that an inclusion is we can have an inclusion, as we all know, that there could be a vapor, this is a liquid, this is vapor, and there could be a solid crystal, and let us say this is our halide. So, the condition which will be corresponding to that is only possible if we have during the time of entrapment. Even if we go back to this diagram, if we consider this diagram, then with the help of this, what we can say here, that this particular fluid which is getting entrapped corresponding to pressure and temperature, let us say it has a content of sodium chloride which will make it, and with further when the temperature pressure is decreasing, there may be a point that is reached somewhere here, in which case in corresponding to that there may be this inclusion in place of just being a liquid, there will be a salt of sodium chloride which will be precipitating from there. So, that means the liquid is attaining saturation with respect to sodium chloride. Now, from that point, when we further decrease the temperature and pressure condition, it will not follow a constant density curve, but it will follow something like a path in which this particular inclusion will have the solid crystal grow a little larger in its size, because the solubility still will fall with the temperature and fall in the pressure and temperature. So, finally, when again it will intersect a point on the boiling curve, this inclusion will give rise to a vapor and the solid crystal. So, this will be a situation corresponding to occurrence of a polyphase inclusion. Now, we will take this up again a little bit more details, and so if we now we are only talking about the simple situation of aqueous fluid without considering the non-electrolyte species, and then we will now the other aspect, that means we are interested in the pressure and temperature condition of entrapment, and the other important attribute that we are interested in is the composition. And as I have said, that because of the dominance of the sodium as the cation and the chloride as the anion, and the most extensively studied system is the water salt NaCl system. And now we will see, is it possible to say something about the compositional characteristic, gross compositional characteristic of the fluid inclusion in terms of the term that we say it is a salinity, or in terms of the total dissolved solid, and the dissolved solid is approximated by sodium chloride. So, this is the binary phase diagram, and I hope that most of you are familiar with such kind of binary phase diagram, and this binary phase diagram is H2O and NaCl, where the temperature is now in the lower side. This is 0 degree Celsius corresponding to the triple point of water, or the temperature at which water solidifies to ice, and in this downward direction the temperature decreases. This value corresponding to minus 20.8 should be noted here. Now, what does it indicate is a binary phase diagram, which can be interpreted or can be understood in a very conventional way, that if we see this is the liquid field, and as the temperature is decreased with any increase in the concentration of sodium chloride, if the further decrease in temperature will make the composition or make the fluid move on this cotectic line. On this cotectic line, the this field is the ice plus liquid. So, on this we will have ice plus liquid as the stable assemblage. With further decrease, so now as we know that this particular liquid will get enriched with respect to the other component, that is sodium chloride, because it is moving to the right, and it will go on moving to the right till the point it reaches, which is marked as E, is the eutectic point. And at eutectic point, as any standard phase diagram interpreted, it will have the complete solidification of the liquid here, and the solids that will be forming are the ice plus a hydrate of sodium chloride, which is known as the hydrohalite, which is NaCl plus 2H2O in its composition. So, this is the water rich side of the phase diagram, and here the liquid will become totally solidified. Now, what will happen if the composition of the liquid is, so this is the eutectic temperature, and the eutectic mixture proportion is 23.3 wet percent of sodium chloride, and this value, which is 26.3 sodium chloride, is the room temperature solubility of sodium chloride in water, which is marked by this vertical line. So, here the other fields, so when we go to a composition, a concentration higher than the eutectic composition, we are on this arm of the binary. So, any liquid whose original composition is here, when the temperature decreases and it intersects the cotectic here, this cotectic will essentially be liquid plus hydrohalite. This is the field in which sodium chloride 2H2O, that is hydrohalite, that is soluble here. So, this is the hydrohalite plus liquid field, and this is the, so here as and when the liquid reaches here, hydrohalite will form, and on further movement of this line, the liquid will become depleted or lesser in concentration with respect to sodium chloride, and it will again follow the same way that reaches the eutectic point, where ice will form along with hydrohalite, and it fluid becomes completely solidified. Beyond 26.3 wet percent, we know that it will be only be halite stable condition. At temperatures above 0 degree centigrade, it will be halite plus liquid. Here it will be hydrohalite plus halite, because any solid halite will be there, will get hydrolyzed, and so this is the complete binary phase diagram on the low temperature side. So, then it tells us that by using of this kind of very simplified diagram, it will be possible to approximate the composition of the fluid in terms of the dissolved solid, which will be sodium chloride. There are standard such depression in freezing point curves, which have been worked out for many other species. The other common species could be potassium chloride, calcium chloride, magnesium chloride, iron chloride. Even there are sometimes bicarbonate, water plus sodium bicarbonate, water plus sodium carbonate, even sometimes it could be sulphate. So, these kind of electrolyte species are also possible dissolved species in the liquid water under crustal conditions of temperature and pressure. So, if we look at such kind of eutectic are known, it is not that they are not known. The water and potassium chloride eutectic temperature is about minus 10.6, water and calcium chloride is about minus 49, water and magnesium chloride is minus 33.6. Fact is that even though these kind of eutectics are known, standard the fact that the crustal fluid has the dominantly sodium chloride as the electrolyte species dissolved. So, the freezing behavior of any liquid which is present in the inclusion cavity can be expressed in terms of the sodium chloride weight percent, thinking that if say for example sodium chloride is some percentage of sodium chloride plus some other percentage of potassium chloride. So, the combined effect of the depression in freezing point will be equivalent to if the whole solid would have been sodium chloride, and this does not introduce much of an error. And so, I have just mentioned a few of the eutectics which are known, but the fact remains that the salinity of the inclusion fluid is always expressed in terms of weight percent NaCl. So, we use a term which is a little bit more specific, that weight percent NaCl equivalent. So, whenever we are doing any freezing study of the fluid inclusions, and what we basically can can see is that in a system that we have described, in a heating freezing system where we can attain temperature as low as minus 196 degrees Celsius, there getting temperature of the order of between 0 to minus 20. So, this kind of eutectic values of course get revised. So, which has been shown here as minus 20.8, possibly has been revised to minus 21.2, but that is immaterial. So, we express them as weight percent equivalent. So, whenever we record, so our whole objective is that we use a microthermometric apparatus and we observe the phase changes that is taking place inside the inclusion in response to the change in temperature in the microthermometric experiments, and we record those as the temperatures at which the phase changes have occurred. And whenever we get such kind of so if we although we will be discussing this in a greater details. So, say for example, a temperature corresponding to a point, say for example here, so which will be something which will be below 0. So, let us say this is minus 5. So, this minus 5 can be translated into a weight percent NaCl, but we know that there could be NaCl, there could be other salts than NaCl, and we can express that it would be weight percent NaCl equivalent. So, now as you could see this table, there are also ternaries like sodium chloride, calcium chloride, water, sodium chloride, magnesium chloride and water, sodium chloride, sodium chloride, potassium chloride and water, and these systems are also important. For example, this water NaCl CaCl2, because possibly other than next to sodium chloride, the other electrolytes which are common in crustal fluid are calcium chloride and potassium chloride, to some extent also magnesium chloride and iron chloride also could be an important species. So, what generally, so you will see that these ternaries are also their eutectic temperatures also known. We will discuss what exactly they are. The ternary eutectic means the same thing. Whenever we have a liquid, we are bringing it to a completely frozen condition, that corresponds to ideally to be the eutectic temperature, and those kind of eutectic temperatures will be definitely different from the eutectic temperatures in case of the binary like sodium chloride, and whatever value, and there are ways to know to reach at the eutectic temperature through the microthermometric experiments which we will be elaborating later. So, the only indication that it can give us about the chemistry of the inclusion fluid is that if the temperature at which the inclusion is coming to a complete frozen stage is way below temperatures corresponding to any of the binary eutectic, then we only can say that this particular inclusion liquid contains electrolyte species other than sodium chloride. Okay, so we will continue discussing on the further on these microthermometric principles in the coming classes. Thank you.